Okay, so we talked about, putting things in perspective. We spent some time talking about local winds just a minute ago. Of course, those are mesoscale. So remember, one of the things that I'm going to hold you accountable is to kind of get a sense of these three different scales of wind. What they all have in common is basically they're created by the same thing. Wind is always created by what we call a pressure gradient force, or PGF. It's basically air is going from a high to a low pressure. So now we're switching gears and going to have to actually talk ultimately kind of three-dimensional. We're going to talk about kind of these global winds. Global winds. Definitely larger than mesoscale. They're macroscale winds, and they last longer too. Okay. So back in, like the slide says, the year 1735, actually, when they were trying to understand winds, of course, winds would be very important back then because a lot of sailing and all that. George Hadley actually came up with this idea of why we have winds like we have. And instead of being ultimately, we're going to come up with something similar to what Hadley did in 1735, but instead of a single cell, we're actually going to have three cells here in a minute. But when it says a single cell or three cells, notice this is in each hemisphere. That's one of the things I fuss about. In other words, Hadley's single cell model actually is two cells. So it looks like this. You're going to see a picture here in a minute, but a player is basically, one of the things you already knew is that the hot spot is usually near the equator, okay? 0 degrees latitude gets the most consistent amount of sunlight throughout the year. So if it's hot, one of the things we said, it will basically, if it's hot, the air actually will rise. That's the ascending part because it's hot. Okay, it will hit, these are terms we've already talked about. It'll go through the troposphere and top off at the top of the troposphere called the tropopause before you get to the stratosphere. And when it hits the tropopause, it's going to basically kind of splat. And so after it splats, a bit's going to head north and a bit's going to head south. And then actually what Hadley had was that clear at the poles, at the North Pole and the South Pole, it would sink, okay, and then it would return. So this is what the picture coming up next, the figure coming up next is Hadley's single cell circulation model. Okay, now one of the things we talked about last week was the Coriolis force, and the Coriolis force comes from the Earth spinning on its axis of rotation. So actually that spin is what Hadley was missing. So this is what Hadley said. Like I said, basically we know the equator is nice and toasty, nice and hot. Okay, so basically you have to think in three dimensions. That air rising, and this right here is trying to show you three dimensions. So basically it's kind of puffed out in the figure. So it rises. This right up here. See, I need to switch colors. I don't know what color is going to show up. Okay, this right up here, that actually is the tropopause. So that warm air hits the tropopause and splats both ways. Some of the air goes this way and some of the air goes this way. And according to Hadley, it would descend here at the poles and then return. Okay? So that's a non-rotating Earth. So instead of a single cell, if you have the Earth rotating, actually we're going to talk through how deflection is what? To the right in the northern hemisphere and to the south in the southern hemisphere because of the Coriolis force. That deflection actually works quite well, and we get three basic cells. So hopefully you can see those three cells. Okay, again, it's kind of three-dimensional. Okay, so here's a cell, and there's one cell hiding up there. So there's three cells in each hemisphere, two hemispheres, so I got 6 cells if you ask me. But the 3-cell circulation model, that's what it's talking about. Notice that whether it's Hadley's 1-cell circulation cell or this current model, the 3-cell circulation model, what they have in common is a nice hot spot right around here. Okay, that's actually where we're going to start. Notice on both of them we have air rising because it's hot, it hits the tropopause and goes both ways. But it doesn't go clear to the equator. So according to the 3-cell model, I'm going to talk you through each of the 3 cells. Remember, there's 3 cells in the northern hemisphere, 3 cells in the southern hemisphere. So the Hadley cell actually is the one that Hadley cells in the northern and the southern hemisphere butt up against the equator. Actually, I'm going to have to kind of switch gears, and the hot spot isn't always the equator. It's actually something called the intertropical convergence zone. But around the equator, we have a pair of Hadley cells that are meeting up. Okay? Basically, things make sense, right? If you think about the equator, you think of tropics and that sort of thing. And you're right, because that ascending air will cool down and basically drop its precipitation. So we do have a band of clouds that kind of follow this equator/intertropical convergence zone. Again, like both models say, that rising air doesn't go any further than the lid of the troposphere called the tropopause. And then it splats and it heads, one leg heads north to finish the Hadley cell in, well, not finish, but to continue the Hadley cell in our hemisphere, and one leg splats and heads south. So we're going to see that actually about 20 to 35 degrees latitude, and actually it kind of varies throughout the year, but in both hemispheres, that actually is going to be the end of this cell. So about 20 to 35 degrees north latitude is where our second cell begins in the northern hemisphere. So about there, actually the air descends, it comes back down, and what were we talking about descending air? And actually the dude on the TV said, as air descends, it gets warm. So actually, this is one of the things I think is really exciting. That descending air there, about 20 to 30 degrees, actually that warm air is dry. And if you look, oftentimes that's where our deserts are. So that's kind of cool. Kind of the end of the Hadley cell. All right. So descending air about, and I know it said 20 to 35, but I usually go 30. I generally, oftentimes will draw this figure. This is the 3-cell model. Okay, this is the equator, so of course we got 0, and up here we have, 90. Okay, so I kind of break it into thirds. It works pretty good. So 30 degrees, and then, 30 degrees, not Celsius, 60 degrees here. Okay, so basically here is what we're talking about. That is where the Hadley cell, basically that air hits the tropopause, it goes this way, and it descends about there. Okay, so that's what this is talking about. Descends, and it's nice and warm and dry. Here, about 30 degrees is a region where sailors used to call them horse latitudes. And the reason they're called horse latitudes was because actually if you're carrying horses and your wind is not enough to blow your sails to get to your location, you dump the horses overboard. No kidding. Really. I know. So if we go ahead and now kind of bring in what we know about the Coriolis force deflecting to the right in the northern hemisphere, this descending air actually, and I have to kind of go 3 dimensionals here, this descending air will splat just like the ascending air splatted. So actually a bit of this descending air is going to go back towards the equator, okay, create a moving air this way, and part of it's going to go back or go towards the poles, and this part is going to be part of the Hadley cell right here. This part actually is going to be part of the next cell. So, but this moving here, deflecting to the right, check this out. That actually, this air at the surface now, not upper, but at the surface actually gives us an easterly wind. Why? Because of the Coriolis force. Why? Because in the northern hemisphere the deflection is to the right. Okay? This actually is our easterly trade winds. And in the northern hemisphere, they're the northeasterly trade winds. They're the northeasterly trades or trade winds. And this is at the surface. Okay? So it's pretty cool. Pretty good stuff. In the southern hemisphere, actually, we could go ahead and make, again, we have 3 cells down here. We could go 30 degrees south, 60 degrees south, pole. And here, we had the air rise, come to the tropopause, come this way, descend here. And so actually, we have a little bit of wind going both ways. This is the other Hadley. We have two Hadley cells. We have a pair of Hadley cells. Now this is deflection to the left. And so if we're going like this, deflection to the left is, I got it going that way. Okay, so actually, as I've drawn them, you have a pair of what we call easterly trade winds, one in the northern hemisphere, one in the southern hemisphere, meeting there. They're each in their own little Hadley cell. Isn't that adorable? So actually, we call these the southeasterly trade winds. Now, the deal is, and I'm going to try to explain this, that I'm putting them kind of between 0 and 30 and 0 and 30, but actually, that location kind of wanders as the hot spot wanders. All right? So like you see here, we see our trade winds meeting up, and actually where they meet up is kind of a slow spot too sometimes, oftentimes called the doldrums, where like the horse latitudes, the winds can be kind of on the light side. Doldrums almost sounds like it's on the light side, doesn't it? But the cool thing too is almost, can you see them on the board where they're coming together, and anything we know where stuff converges, basically it piles up, and what's it do? It goes up. So that again kind of supports the air begins ascending there where that's piling up, where the trades are meeting. All right, so those are the Hadley cells. Let's meet the next cell, and actually that's us. I've used different textbooks throughout the years, and I can't remember if your textbook uses this term or not. But I'm thinking it doesn't. But there is a name for us.
Ferrel cell.
Yes. 2 L's? Yes.
1 L, 2 R's.
Okay. All right. We are in the ferrel cell. So there's a ferrel cell up there. There's a ferrel cell down here. Sure? Okay. So here's the deal then. And let's look at it this way. Basically, I said the air rises here at 0, goes to the tropopause, falls at 30, and some of that goes this way and some of it goes this way. Now, if we go this way and we have deflection to the right, guess what? We have a westerly wind. Anytime you see here the word east, west, north, south, and they are describing a wind, they're describing the direction it's coming from. So that actually is our surface westerly wind. These are our mid-latitude westerlies, and they have them down here too. Again, these are at the surface. Latitude westerlies. A classic question for me is to ask you where are we with regard to the 3-cell model and our prevailing wind. So, of course, we are smack dab clearly above 30. So 30's here. Okay, 60's here. That's the ferrel-ish cell. In the southern hemisphere, it's deflected to the left. So actually, you kind of have to stand up like this and go down like that and go to the left. And actually, you go ahead and you get a westerly here too. If you're like me, you have to stand there and do it. Okay. So I mentioned you can kind of split the globe up into 0 to 30, 30 to 60, 60 to 90. That's kind of how I do it. I know it's kind of rough there. But there about 60, it's the end of the ferrel cell. So basically, we need that air to ascend. So here about 60, this air is going to go up. And so I'm not going to put it on there because I'm kind of keeping with surface winds there. So, but the air goes up, again hits the tropopause, and a little bit of it goes this way and a little bit of it goes that way to complete the ferrel cell. So the third cell is the polar cell. Again, these are in both hemispheres. So to me, there's 6. So a good way to kind of think of the polar cell is basically where it's very cold up here. Basically, we have this cold descending air at the poles. Okay, it's cold and it's dense and it's descending. And think of that. So basically, we have air coming down, going in all directions. Okay, so again, deflection is to the right. So actually, if we're going to do that, our surface wind is going to be another easterly. This is our polar easterly. I'm going to try to convince you that even though we kind of have surface winds of trade winds are easterly, Mid-latitude winds are westerly. Polar winds are easterly. Up at upper elevations, we have a strong wind from the west at upper elevations, but these are surface winds. So a few things. This talks about the polar front. The polar front is basically right here where you have clashing warm and cold air. So the polar front is between the polar and the feral cells. So busy slide, but this kind of summarizes everything I just talked about. Okay, three-dimensional. So if we kind of see where everything is, this would be a good one to put under your pillow. Yeah, I can tell that yeah, it is just one L, isn't it? Your book definitely has that term. A polar cell. And at the surface, we have, it alternates the easterly trades, the mid-latitude westerlies, the polar easterlies. We said that the horse latitudes was between the Hadley and the feral cell. We said the doldrums were here between the two Hadley cells. Okay, so those are all things that we talked about. One of the things we're still going to talk about soon, very soon, is this idea of basically where we have the Hadley and the feral cell meeting, we end up with a high pressure. That high is created by that descending air. Okay, and here where we started the whole process, near the equator, our hot spot, actually we have an ongoing low pressure. That's called the equatorial low, and the subtropical high is between the Hadley and the feral cells in both hemispheres. All right. So this is like what's happening at the surface. Notice by default we have that kind of low pressure here where things got started. Like I said, we have a high pressure. This would be between, I'll just go ahead and put H for Hadley, F for feral, and P for polar up there. H, feral, P for polar down there. Now, this is the first time they introduce you to something I think is important called the ITZZ. It stands for Intertropical Convergence Zone. Intertropical. And you can almost see where the convergence comes from. What's converging there? The northeasterly trades and the southeasterly trades. All right. Notice it says idealized. I'm actually going to compare the real deal to this deal, and what we're going to have to add is land masses and large bodies of water. So that's the idealized, and this is really what it does. Okay. So, because one of the things we know as a player is that the oceans and the land masses don't heat up and cool down the same way, and so that's actually kind of what you're seeing. But we're going to talk more about, as we talk about ocean currents and El Nino and La Nina here in a minute, okay, we're going to talk about these. Should choose a different color than red. Let's see. Yellow? Nope, because there's yellow too. Okay, anyway, these right here. Remember I said, I kind of stood here and looked upside down, and I said that if we look at our neck of the woods, North America, and we look at the Atlantic and we look at the Pacific, I said these ocean basins have basically currents and prevailing winds. Actually, it's the wind that creates the current. So they have currents that go clockwise, okay, right here. And actually that's why we end up with kind of cold water along our west coast, and actually that's why we end up with warm water along our east coast, okay. Direction that air moves around a high, and those are the highs. This high right here that you see on this map up here is what is creating this clockwise motion. What is that? It's an anticyclone. High pressure. It goes clockwise. What's it created from? It's actually created from the descending leg of our Hadley cell. Semi-permanent highs. All right. So the hot spot. And it's only like the last few years I've been calling the intertropical convergence zone the hot spot, but I really think it is. Hot spot. That's basically what I've been calling the equator. It's what Hadley said kind of starts the thing where the air ascends in the first place, and it hits the tropopause, and it goes both directions. So the location of the intertropical convergence zone has to change when as the Earth orbits the sun, and basically kind of the subsolar point, I think is what we call it, where the most intense rays of the sun are changing as the Earth orbits the sun and its tilted axis of rotation. So as the hot spot changes, everything else has to change. So I have some maps to kind of show you what that looks like. Okay, so those would be the macro scale winds. Okay, your trade winds and your westerlies, your polar easterlies. Okay, a little smaller than the macro scale would be these mesoscale winds. So we have kind of a couple of semi-permanent bands. We have the semi-permanent low basically associated with the intertropical convergence zone, and then we have a high associated with the where the Hadley ends, wherever that's going to be. It migrates throughout the year, about 30, but it migrates. And then actually we're going to have another low, like the intertropical convergence zone, up between the ferrule and the polar cells. Okay, so let's see if we can find them. Notice this is in January. So, of course, January is winter time in our hemisphere. Okay, so let's see. I bet you guys can see the high pressure, semi-permanent highs. Okay. And see if you can see, especially in the northern hemisphere, can you kind of see the clockwise motion? These are winds. These aren't currents. All right, these are currents. I think these are winds. Okay. Yeah. So can you see also the polar, the low, semi-permanent lows up there? And semi-permanent low down there. So that was January, and this is July. And here in a minute, I'm going to show them side by side. Because as you might imagine, that hot spot actually moved north. Okay, and everything kind of migrated with it. If you've ever heard of the Bermuda Triangle, actually that's the name of that semi-permanent high in the summertime over here. So again, clockwise motion, clockwise. Around this low, we see kind of maybe counterclockwise. Okay. In the southern hemisphere, we should see counterclockwise around the highs and clockwise around the lows. Again, thank the Coriolis force. So here they are side by side. And this slide, this is one of my favorite titles of my slides. It's called The Wandering Intertropical Convergence Zone. There will definitely be some questions on your test about intertropical convergence zone. It's such a player. It's where your Hadley cells butt up with each other. Definitely not straight. If I were to circle where the equator is, where zero latitude is, it's right here and here. I bet you can already see that. Okay, so it definitely just doesn't go straight. It migrates north in July. Intertropical convergence zone. Remember we said that that's where actually the air is ascending, and as it ascends, it will expand, and as it expands, it will cool. And if it's moist at all, which that's a lot of ocean, right? If it's moist at all, then when it cools, it can reach the dew point temperature, and we get a band of cloudiness. So I bet you've heard of monsoon seasons, and monsoon seasons actually have to do with what we're talking about. Right? A monsoon, if you have a location that experiences monsoon seasons, actually it's a pair of seasons. It's a rainy season and a dry season. So in general, the dry season is in the winter and the rainy season is in the summer. So I think on my slides I had both of them, prevailing wind from the land to the sea, and it really should be for the summer. You're going to see it here in a minute that it's a prevailing wind is from the sea to the land. That's why it's so wet. So what happens is that intertropical convergence zone wanders and it actually moves this prevailing wind. You might be most familiar with monsoon seasons actually in Asia, but actually I'm going to show you there on our in our southwest in North America, we also have we have a rainy and a dry season. Monsoon seasons these pair of seasons have to be related to the fact that the intertropical convergence zone is moving and it moves the prevailing wind. I'll show you what that looks like. So we're going to see a pair of pictures. This is the purple line again is where the hot spot is in the summertime. Okay, so you can see kind of that warm, moist air. You can see the converging easterly trade winds, right? And so the air is ascending there and it can drop. Not only is the air ascending there, but it's nice and moist air from the oceans. Okay, so that is actually where they're going to get dumped on. The Himalayan mountains is what does the orographic lifting, right? Orographic lifting, yep. So now find the intertropical convergence zone and look how far to the south it's moved. And those red lines are showing you which way the wind prevails or generally blows at that time of year. Okay, so now we have the converging easterly trade winds clearly south of the Himalayan mountains. So basically, and one of the things we know about being on the leeward side of mountains, right? Okay, if you're over here, the leeward side of that mountain, basically you're going to have dry conditions. Okay, so this is their dry season, and it's all because, and I don't have these side by side, but it's all because of that wandering intertropical convergence zone. So let's talk about North America and how we get actually the wandering intertropical convergence zone gives us a dry and rainy season. So the thing that actually you need to think about is, let's see, remember we talked about air can actually be lifted vertically if it goes from the ocean to hitting land. So that's actually kind of, I think, the lifting mechanism for this. Oh, we do have some mountains there. So you see the climatogram that we actually looked at in earlier chapters. Added to the climatogram is this information down here showing you precipitation. And you definitely see in July and August, a fair bit of precipitation falling.
I don't know how fair that actually is. It's actually only like 2 inches.
Oh, well, 2 inches compared to trace amounts a couple months earlier. Okay. So that is your second monsoon. So the next thing to talk about is what I told you, that at upper elevations we just definitely have something other than these the trade winds and the mid-latitude westerlies and the polar easterlies. Upper winds generally will blow from due west ultimately to due east. Okay, and the reason is that, and actually I changed the word, I don't know if it was right on your slides, but just this afternoon when I was getting ready, instead of any, it should be the word upper. Generally at upper elevations instead of any. Generally at upper elevations there's a pressure gradient from the equator towards the poles. So if we grab kind of try to be three-dimensional about this whole thing. Okay, so it's saying that at upper elevations there's the equator is got a high pressure, okay, and the poles have a low pressure, high, low, see. Okay, so we're going to go like this, right? Okay, deflection is going to be the right in the northern hemisphere. Okay, so that's why we have at upper elevations this westerly wind. Okay, I have to convince myself too. You might be wondering, how do we get this upper level high pressure and low pressure? And actually, it has to do with temperatures again. If it's generally hot near the equator, and of course cold near the poles, we said that cold air actually is more dense and should be a higher pressure. But what happens is basically those air particles sink, so basically it's all dense down here and it gets low density up here, okay? And here with this warm air, basically we have, our particles are more uniform throughout. So we have a low pressure up here and a high pressure here. That's how that's created from our cold temperatures at lower elevations. So this is actually showing you, I think, something we talked about last week. Geostrophic winds is basically wind that actually is going between isobars. Here we have our isobars here. Okay. And so it's in the groove, so that makes it geostrophic. And it is actually going due, it's like we have north here and south there, right? It's actually going due west, or it's a westerly wind. It's going due east. Okay, and that deflection is because of the spinning of the earth. So all those rules we talked about the Coriolis force last week, you'll need to know. So this says that the pressure gradient force will increase as you go up in the troposphere. So we said pressure gradient force increase gives you a stronger wind. So basically the winds get stronger and stronger as you go up in the troposphere. Notice, and I had to look this up a few years ago just to convince myself, but once you transition beyond the tropopause into the stratosphere, actually your winds begin to decrease because your pressure gradient force is less. So speaking of upper level winds, we have a pair of jet streams. One is stronger than the other. But what both jet streams have in common is that they are kind of a tube of fast-moving air. You can kind of see, as they're depicted here, is kind of a blue and an orange tube of fast-moving air. In this case, they're kind of showing them a little wavy. They don't always have waves. Sometimes they're kind of what we call zonal. This is kind of more meridional. Okay. If you're flying a hot air balloon, you definitely want to know where the jet streams are to kind of get you quickly from one location to another. So I have a video, I hope. So sometimes your jet stream, whether it's the polar jet stream or the subtropical jet stream, sometimes it's going straight, kind of like no waves. But oftentimes when we look at upper elevations, actually we kind of see the wind kind of going in these cool little wavy patterns at upper elevations. It's not just straight between the isobars at upper elevations. Those gentle waves, usually gentle waves, are actually called Rossby waves. And they encircle the Earth. And so like this says, sometimes you can have 3 to 6 kind of these waves that are kind of in your jet stream. So if there are waves or if there are no waves actually is a player in, like what Dirk was saying, what's going to happen at the Earth's surface. This says the waves create, enhance, and direct weather system. It's exactly what Dirk was showing you. When he kind of showed a healthy sort of wavy sort of pattern, you just picture with these are called Rossby waves. If they're in place, you just kind of picture you're going to have an alternating high, alternating low, which is all going to go that way. And you get new weather. When it's straight across, we call that actually zonal flow. Then your weather is going to be pretty darn constant, which could be good or bad. Okay, so we see a little bit of wave there. And this is talking, yeah. So if it stalls out, like he was saying, if it's stalled out with a low pressure, you're going to get lots of precipitation. If it stalls out with a high pressure, you're going to have drought conditions. And actually, that's all consistent with what we talked about, I guess it was last week, when we talked about on your barometer at home. A lot of times, your barometers, if it says high pressure, you say fair skies, clear skies. Okay, low pressure, cloudy, right? That's kind of the name of the game. So we have these two options with the Rossby waves, or I guess I should say flow aloft. Kind of at upper elevations, what we call zonal flow, I kind of think of like, I can never remember the word meridional, so I always think zonal like somebody's trying to throw a pass to a football player, between football players to the end zone. Okay, that means it's basically going straight. Meridional means it's wavy. Okay, it kind of has a little bit of wave to it, north and south flow. So again, zonal flow, basically not much of a contrast. Okay. Your weather's going to be consistent. Basically, what you have, you're going to be stuck with. That was the second thing that Dirk said, kind of the second scenario, when he showed, if you remember, his jet stream was pretty straight. With waviness, actually, you're going to expect kind of an alternating weather conditions. And I haven't said it, but this actually emphasizes, too, with that kind of waviness, the waves going up is going to transfer heat to the poles. The waves going down is going to transfer in the northern hemisphere. The waves going down is going to transfer actually cold air down to the equator. So I think on the next slide, or maybe not on the next slide, but just start to get to be looking for these waviness, these meridional waves, alternating lows and highs. Again, I think it was last week when we talked about troughs and ridges. And actually, I don't know if I can get this right. Our highs were ridges and our lows were troughs. I'm going to write that on here. Highs were ridges.
Yeah.
And our lows were troughs.
Yeah, because if you look at the way that it's going, the low pressure, for it to maintain its counterclockwise-ness, it has to be on up high, so it would create the trough.
Okay, that sounds right. And so highs, like it says, think of clear skies, and lows, think of precipitation, just in general. Thank you.
No, I'm not going to be your dirt.
So, if you've ever heard of an Arctic air mass, if we've ever been under the influence of an Arctic air mass, yes, we have. So honestly, I'm going to kind of try to show you in a series of pictures how the jet stream kind of gets so wavy that basically a chunk of cold air that was up there near the Arctic Circle comes on down, pinches off a cold bit of air and comes down. So the way you read these is it goes from left to right and top to bottom. So this is 1, 2, 3, and 4. And you can kind of see here, I'd say it's pretty zonal there. Zonal flow, not much waviness. Okay. We have a bit of a kink here that actually, if you look between 2 and 3, that wave there is actually going to be pinched off. And so here is where you get a chunk of air that really should have been up here, down where it's cold.
What the polar vortex is.
Yeah, the polar vortex, I'm thinking the polar vortex is kind of right underneath or associated with the polar jet stream. Basically, we assume that the polar jet stream is going to kind of, like you see the blue here, kind of confine that stuff in the Ferrell cell up around the poles.
What is the difference between a polar vortex and great wall?
You know, I don't know. Sorry. I really don't. So now switching gears. Actually, this is a good time for a break. We're at 1/4 So let's go for another break, and we'll pick up with oceans and El Nino and La Nina momentarily.